Today we're starting our new chapter over thermodynamics. So, what is thermodynamics? It's the study about how heat energy is transferred. Okay. In order to talk about this heat transfer, we have to have some method of recording it or a scale to use to know how much heat energy is being transferred. So, we use temperature. Okay. In physics, adding or removing energy usually results in changes in the temperature. Okay, when you touch an object that feels warm, okay, energy always flows from warm to cool. Just like water flows downhill, it's going to go from warm to cool. So if the phone feels warm, the heat energy is leaving the phone and flowing into my hand. Likewise, if I have an object and it feels cold, okay, if it feels cold, that means my hand is warmer than the cup. So heat energy is going to flow from my hand into the cup. Okay. It always flows, heat energy flows from the warmer side to the cooler side. So temperature is proportional to the kinetic energy. The kinetic energy of all the particles, the atoms, and the molecules that make up the substance in which the energy is either being transferred from or to. So the more energy the particles have, the higher the temperature. Okay. For gases, we're only concerned about the translational kinetic energy. That's all we're worried about because they're not being held down in any way. Okay, the particles are moving around. The warmer the temperature, the more these particles are just moving around. When we talk about other substances such as solids, okay, they're in a lattice work. They're more structured. So they're not free to move around as much, but they can vibrate. The particles vibrate. So there is a vibrational kinetic energy, and there is potential energy in the particles that are not moving as much as they could, if that makes sense. So we're down to the atomic level, thinking about the atoms and the molecules that make up the substances we're referring to. So we're talking about the kinetic energy of those particles. We call that internal energy. Okay. So internal energy, think of it as the atoms inside the substance that makes up the substance. And it's symbolized by the big U, the big letter U. The change of internal energy is delta U. Remember, delta means the change of. So for ideal gases, because nothing's holding down the particles, the internal energy is solely based on the temperature. Warmer it is, the more they can move around. So that gas has an internal energy. If it's a solid object, there's other factors like if the particles are in some kind of lattice work or can they not move past each other, that type stuff. So gases are a lot easier. So temperature is only meaningful when it's stable. When the temperature comes to a certain point and doesn't change anymore, then we can measure it, and it's in thermal equilibrium, the state in which two bodies in physical contact with each other have identical temperatures. So when I say no net energy exchange, let's say this cup is the exact same temperature as my hand. It's not going to flow from warm to cool because they're the same temperature. There's no heat exchange, there's no heat flow. And we use this idea for the basis of a thermometer. Okay. I don't have a thermometer here at home, one of the old fashioned glass ones. So we're going to use your imagination. This ruler is the tall part of a glass thermometer. I know you've all seen a thermometer, okay? The old-timey ones, the ones that are not digital. So here we have a tube of glass, okay? There's a tube of glass, and at the bottom of that tube is a glass bulb that has some kind of substance in it, okay? And we're going to use the principle that in most objects, as they get warmer, they get larger, they expand. And most objects and liquids, when they get cold, they condense, they contract, they get smaller. It's this thermal expansion and this thermal contraction that is the idea behind a thermometer. Okay, we'll come back to the thermometer in a minute. How much the object, the gas, the liquid, whatever it is, the amount that it can expand and contract is given a coefficient, okay, the coefficient of volume expansion. It's an indicator of the ability of a substance to change volume. So it would make sense, since the gases aren't held down, they can expand the most because their particles are just roaming free, okay? So gases are going to have a lot larger coefficient of volume expansion than solids, okay? Like I said before, most things contract as they get colder. The only exception to this that we're really going to talk about is water. Water is unique, okay? Just so happens that we're mainly made of water and there's water covering our earth. But water is a little bit different. Water actually expands when it freezes. It does the opposite of what you expect. If you've ever filled an ice tray full of water and you put it in the freezer, you come back later when the ice is frozen and the ice is kind of sitting above the level of the ice tray, okay? It's because the water molecules are moving around. It's a liquid, okay? In order to freeze, those particles have to align themselves into a predictable lattice. Having to rearrange and go into an ice lattice, let's call it like that, it takes more room. So the ice actually expands. It is unique. This is the reason we do not use water in thermometers. That'll make sense in a minute, because it does the opposite of what we expect it to do. So, water being unique, this is why ice cubes float. Going into that lattice work, they're less dense than the water around them. Therefore, ice floats. Also, canned beverages, they have to expand because they're made of mostly of water. Okay, they're in a can. The can doesn't give, and so the ice, the frozen soda water, is going to rupture the can. It's going to spew everywhere because it has no place to expand. It's getting bigger as it freezes. Okay, back to the thermometer. Excuse me. Thermometers use some property that changes as temperature changes. Okay, the old fashioned thermometers, we used mercury. Mercury is dangerous. It's a controlled, dangerous substance. Okay, so now we use the alcohol, and we usually put some kind of red coloring in the alcohol so that we can see it. Otherwise, it's clear and hard to read. But so take it, we have a tube of glass here, and there's the glass bulb at the bottom. Okay, imagine there's alcohol in that bottom tube. As that, okay, so say we're going to add heat to that alcohol. It's a liquid, it's going to start expanding, but it's in a glass tube. It has nowhere to expand to except up the glass tube. Okay? Likewise, when this alcohol loses loses heat and cools off, it gets sucked back down into the glass bowl. You get the idea? So, the substance here, in this case alcohol, it heats up, it goes up the tube, it cools down, it's sucked back down. All we have left to do is put some kind of scale along this so that we can refer to whatever that temperature is and give it a value. So, hence the Fahrenheit scale, the Celsius scale, and Kelvin. So, Fahrenheit is used here in the United States. We're one of the only countries that still uses Fahrenheit. On the Fahrenheit scale, fresh water will freeze at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit. The exact same thermometer changed the scale, okay, to Celsius. Most European countries and Canada and those type countries use Celsius. On the Celsius scale, kind of think of it as the metric system of temperature. It uses 0 as freezing and 100 as boiling for water. Okay, so Fahrenheit and Celsius. And then how do you convert back and forth? You're going to be doing this tomorrow, so make sure the equations end up in your notes. To go from Celsius to Fahrenheit. So you're going to go from Celsius to Fahrenheit. You take your Celsius temperature, you multiply by 9/5. You get that answer, and then you add 32. Likewise, to go from Fahrenheit to Celsius, you're going to do the backwards. You're going to take your Fahrenheit temperature, you're going to subtract 32, and then you're going to multiply by 9/5, which is the opposite of the one above. So basically, you're doing the opposite. You're going back and forth. Okay, you're going to need to do this tomorrow. And then if you think back to chemistry, you should have talked briefly about Kelvin. Kelvin is based on absolute zero. Absolute zero is the temperature in which all of the particles, the atoms, the molecules of a substance stop moving. Okay? We have never been able to achieve absolute zero, but we've come pretty darn close. So instead of saying the temperature at which the object's energy or molecules stop, we say the energy is minimal because we haven't quite attained it yet. Okay, so on the Kelvin scale, water freezes at 273. We can drop the 0.15 for now. We're going to keep it easy, 273. Water boils at 373 Kelvin. Okay, it's easy to go from Celsius to Kelvin. You add 273. Boom, you're done. To go from Kelvin back to Celsius, you subtract 273. And then if you're going from Kelvin all the way back to Fahrenheit, you have to go to Celsius first and then convert it to Fahrenheit. And you'll be doing that tomorrow also. So, like we were talking about, 3 thermometers identical, okay? The same amount of heat's been applied to the liquid, and they're the same height up the side. The only difference is they have different scales attached to different things. So let's say 0 degrees Celsius, this middle one. To go from Celsius to Kelvin, you add 273. So 0 is going to be 273. 0 is where water freezes on the Celsius scale. If we go to Fahrenheit, it's going to be 32. Okay? So all you've changed is the scale. You haven't changed the temperature at all. It's just how we describe that temperature. What scale do we use? Okay, that's it. Get the notes copied into your journals, get them submitted on Schoology, and this will be actually your second grade of the fifth 6 weeks. I decided to use the vocab that we did at the end before we went on the snow break. I'm going to count it towards the fifth 6 weeks. So get that done, get them submitted, and I will talk to y'all later.